Hey there! Today we'll look into a new video generation work, reward forcing, efficient streaming, video generation with rewarded distribution matching distillation. As we know, generating video currently faces major issues regarding length and dynamic scene consistency. The big challenge is, can the video follow the prompt well and expand on what has happened before without image jittering, strange movements, or the background suddenly changing? This work provides a solid way to achieve dynamic consistency. The source introduces reward forcing, a novel framework designed for efficient streaming video generation that specifically addresses the issue of diminished motion dynamics found in previous methods. This framework utilizes three main technical innovations: EMA-Sink, a state packaging mechanism that uses an exponential moving average, EMA, to update fixed-size tokens with evicted data. This prevents over-reliance on just the initial frames and maintains long-horizon consistency without increasing computational costs. Rewarded distribution matching distillation, ReDMD. This feature uses a vision language model, VLM, as a reward function. It prioritizes samples with greater dynamics during the distillation process, substantially enhancing motion quality. Causality, CAUVID. Unlike standard bidirectional attention, this framework enforces strict causality. The generation depends only on previously generated frames within a window-sized limit, ensuring the model respects the temporal order of events while remaining efficient. Quantitative and qualitative experiments show that the combined method achieves state-of-the-art performance in terms of both video quality and real-time inference speed. Let's jump right in. So, the model can essentially be torn into two parts. Part 1 is the historical dynamic scene preserving component. Instead of just keeping a static head, often called the sink parameter, standing at the beginning of the video, this model uses the exponential moving average, EMA, to average up the historical generated scenes. Whenever the buffer is full and frames are ejected, a portion of those frames is averaged into the sink tokens. This ensures the model keeps tracking the history of the generated frames. Within the other components, it consists of the historical generated scene, the maintained buffer, and the part of the scene that is currently being generated, starting with noise tokens. The next part is relevant to the long generated frames. Previous work introduced the forcing concept, where the student model is trained on KL divergence against a teacher model. The teacher is a fixed weight model that has access to the ground truth of the full-length original video. The current student model attempts to learn the true distribution of how the video should develop. However, this work adds a visual causality component. We can incorporate an additional model to rate the quality of the current video fragment. What this paper proposes is adding a reward on top of the forcing. This is a score that balances the trade-off between the quality of the motion and the consistency of the dynamic scene. This is what they call reward forcing. Let's look further into the attention mechanism. Previously, for a diffusion transformer to generate video, the context length was fixed. To generate a longer video with unlimited frames, we rely on a sliding window. First, strictly speaking, in standard window attention, the model only keeps the history within a fixed window size and discards the rest. Ideally, we can say it forgets what has been generated, so it may repeat itself or fail to follow the initial context. A quick fix used in previous work is the attention sink. Instead of just depending on the recent window, it also keeps the first frame permanently. This helps the model remember the beginning. However, because it discards everything in the middle, there is still inconsistency in the dynamics of the video. Now, let's look at the proposed EMA-Sink method. Instead of discarding the frames that go out of the window, and instead of only keeping the first frame, it performs an exponential moving average on the evicted frames. This compresses the information into the sink tokens. As a result, the generated video retains a better formula and knowledge of what has been generated, allowing it to keep generating consistent, dynamic, and reasonable frames. So now we can have a look at the scene tracking performance. On the left 4 parts, we see the baselines. You can see the length of the scene consistency struggles. Either the background becomes blurry, or the movement in the scene is inconsistent. On the right, looking at the current work, you get a human walking. It looks like what we expect in reality. There are still minor issues. Occasionally, a hallucination might pop up, but basically, the quality is highly improved. As you see, the example of the drumming underwater is particularly impressive, showing complex fluid motion that remains consistent. As we can see in the data, the quality of the generated short video is the highest among competitors. When it comes to larger, longer videos, over 1 minute, the smoothness is not the absolute best, but it is highly competitive. However, when we look at the dynamic score, we see a very high boost. The model achieves the best total scoring on the V-Bench long evaluation scores. Using the Q1-3BL model to score the visual and dynamic quality, this model gives the best performance over previous SOTA models. As we have seen that its performance is better than self-forcing and long life methods, now we will see how fast is it. If it generates 9 new frames per step, it can reach 23.1 frames per second. This is far better than the long life and self-forcing methods. As a result, this new method not only generates faster, but also reaches better quality. Finally, it performs well with editable quality, rather than being confined to the first prompt. As we can see in this example, for 0 to 5 seconds, the video shows an empty glass on a rusty wooden table. But for 5 to 10 seconds, the prompt changes to dark coffee stream into the empty glass. Instead of being constrained by the first task, it fluently transitions to generating the dark coffee pouring into the transparent glass. To wrap up, reward forcing represents a significant leap forward in the field of video generation because it solves the impossible triangle of speed, length, and consistency. By moving away from static attention sinks and adopting the EMA-Sink, the model effectively compresses memory rather than forgetting it. By integrating rewarded distribution matching distillation, it solves the motion degradation problem. When we combine this with strict causality, we get a model that is not only SOTA in quality, but is also fast enough for real-time applications. In short, this work moves us away from generating short, fixed video clips and towards a future of endless, consistent, and controllable real-time video streaming.